class. I'm Dr. B, your chemistry teacher. Today, we are going to be discussing energy of activation. Energy of activation, and some of you call it the activation energy. So, it do not matter whether it is written as energy of activation or it is called activation energy. And what is interested in today's class is that we want to calculate the energy of activation. Do not forget to share this class and play. When you share this class, do not also forget to ask your friends to do what? To also subscribe. So when this class is up in the internet, they're gonna have this particular class popping up in their phones. And then do not also forget that we have also a Facebook page, Dr. B Chemistry or Science Classes. And do not also forget that you can share to your friends and other academic platforms or groups. And do not also forget to let them know that they can follow so they can have these classes coming up on their phones as soon as we put them on. Thank you very much. Now we're going to look at energy of activation. But the question is, what is energy of activation? What is activation energy? All right. In our secondary schools, we were told that activation energy is simply an energy barrier that needs to be removed for a chemical reaction to take place. Of course, that is what we used to know. Okay, it's an energy barrier that needs to be removed. But today, I'm going to define it in a very simple term that activation energy or energy of activation is simply that particular extra energy that is required to be supplied to reactants for a chemical reaction to take place. That is just what it is. It is an extra amount of energy that is required to be supplied to reactants, reactant molecules for a chemical reaction to take place. And we could just explain that in a very simple term. Imagine you have something that is in front of you and you need to exert your punch on it for an impact to be felt or to be created, but there is something standing on the way between you and that thing that needs that impact from your punch, from your blow, so that there could be a reaction at the end of the day. Now, that particular extra energy required by that punch you want to supply to remove that barrier that is standing before you, so that that impact of that punch will be felt by that other substance or that other thing that is actually the right one to receive that punch, to feel that impact, that extra energy the punch needs, okay, to overcome that particular barrier standing before it, so that that thing we're going to get that impact and have a change, is what we call activation energy. So I will simply put again and say it's activation energy is simply that extra energy required by reactant molecules for what? For a chemical reaction to take place and product needs to be formed. Now, if that is true, then how do we answer this question that says for a reaction A plus B to give us a P, which of course is product, the slope of the plot log K versus 1 over T is minus 20 kilojoule. Or, of course, sorry. What is the energy of activation for the reaction? Yeah. You have a chemical reaction where the reactants are A plus B, giving you P, which is the product. The slope of the plot, log K versus 1 over T, is minus 20 kilojoule. What is the energy of activation for the reactant? So you are expected to calculate the extra energy that is required to do what? Required by this reactant to be able to break through the barrier standing before it to form what? A product. That is all that is needed. Now, in this question, it's quite a practical question. So you have a slope given. That means there is a graph. For every activation energy graph, it is a straight line graph. So what it means here is this: you have a graph, and in this graph that you have a slope, and then this is your slope, and we are told that your slope is minus 20 kilojoule. That's what we are told. Of course, with this kind of a graph, it means that this here is of course your intercept. Okay, it's your intercept. So you have a plot of what? Of the log of k against what? 1 over t. And in this kind of a graph, how do you calculate the extra amount of energy needed by these two reactant molecules to overcome an energy barrier that will give you a product? And to calculate such an extra energy, which you call the energy of activation, you need to understand the nature of this graph. It's a straight line graph. That means y is equals to mx plus c, where of course your m is your slope, which is this. That's what it means. So how do we fit this? And to what equation are we going to fit this 20 given to us here as the slope in order to calculate or determine that extra energy that is being determined, expected from us as the activation or energy of activation? To what particular equation can we do this? But remember that the only equation or the only viable equation that is required for you to calculate energy of activation is the Arrhenius equation, in case you do not know. The Arrhenius equation is the only viable equation for now that you can be able to use to calculate the activation energy. So now we are going to introduce the Arrhenius equation and use that equation to calculate the activation energy or energy of activation. Now join me, let's do this. I'm going to clean this. Alright, now with this, the Arrhenius equation, is the only equation or the only viable equation you can use to calculate, to determine your energy of activation or activation energy, as the case may be. And what is the Arrhenius equation like? Arrhenius equation is simply written as K is equals to what? Is equals to A to the exponent of minus EA over RT. That is the that is the Arrhenius equation. Yes. Where K is simply your rate constant. So it means that this equation runs around, the Arrhenius equation runs mostly around the kinetics, chemical kinetics, and not because the transition state equation run around the thermodynamics. Okay, so the Arrhenius equation runs around the chemical kinetics. So K is the rate constant of the reaction. And then the A, okay, let's say K is what? The rate constant of the reaction. And then A is the pre-exponential factor. The pre-exponential factor, or you can call it the frequency factor, or even the collision factor. And then the EA is your activation energy or the energy of activation. Okay, while your arrow is your gas constant, and the T is your absolute temperature. This is how the terms are defined. So K is your rate constant, and then A is your pre-exponential factor or the frequency factor or even the collision factor. So it simply defines the amount of active elements or active molecules in that particular reaction or in the particular reactants that allow for the reaction to take place. So if you are looking for the active molecules that took part in the collision at the reactants for the chemical reaction to occur and product being gotten, then you are going to be looking at what? At the pre-exponential factor. And then this is the activation energy. Now the whole of this define that minimum extra energy that is required for the reaction to take place. The whole of this factor defines that minimum extra energy required by the reactants for the reaction to take place. Now, how do we fit in the minus 20 kilojoule that is given to us as slope? Now, it is necessary for us to note this, that from this equation that we have here, we can simply remove the exponential sign that we have here and introduce immediately the natural logarithm. It is possible. So that means that we will now have the log of k is equals to the log of A minus activation energy over R root T. That means we have that. Or rather, sorry, not the log, the natural logarithm. So it is the Lin sign. Is the Lin sign. So we can possibly have this equation being rewritten in this form. And in this way, we have been able to remove the exponential form and introduce the natural logarithm on the k and the a, the pre-exponential factor and the rate constant. But that is not all. I hope you know that when you say ln k or when you say ln x, it's same thing like saying 2.303 to the log of x. It's the same thing. That is, you are changing from this natural logarithm to the log. So you simply do what? Remove the natural logarithm Lin sign and introduce 2.303 log of that particular factor. So if that is true, we can do that for this equation. So we can simply say this equation can be written as the log of k equals to the log of a minus what? E a all over 2.303 what? R T. That's what it means. It means that we can do this because once you remove the natural logarithm of L of Lin to a particular factor or number, you must introduce 2.303 as a constant of logarithm to that particular number. And if we do that, then we can simply say that where we have a Lin of x, which is our factor, which is this, which is where we have the activation energy. So we can simply introduce this. Now, with this equation that we have here, we can simply understand the fact that this equation can be written in a graphical form. Do not forget that that question too said that there is a plot of what? Plot of log of what? Log of k against what? 1 over t. That's what it said. So if there is a plot, this is how the question said there is a plot of log k against 1 over t. That is what the question says. And that there is a slope that is minus 20 kilojoule. There is a slope that is minus 20 kilojoule. That's what the question says. And if it is in this form, that means that this particular line is a straight line graph. And for a straight line graph, we can define that mathematically as y equals to mx plus c. Yes. So we can introduce this to this equation. And when we do that, this is what we're going to have. So we can simply say that y is equals to mx plus c. That is for a straight line graph, which we are being given in the question. Where, of course, our y is this. And then our a is the intercept. And then the whole of this is our m. Okay, our y is the log k, our c is the intercept, and then there's a log a, which is the pre-exponential factor, and the whole of this value is this. But the plot was between log k and 1 over t, so this t can be removed. That means that we can simply say if this is the slope, this implies that the slope, which is m, will be equals to what? Minus EA all over 2.303 RT. But since the graph was plotted against log k and 1 over t, we have to remove the t. So this can also be written as minus EA all over 2.303 R times 1 over T. Times 1 over T. So this 1 over T is this plot that we have here. So this becomes our slope. And if this becomes our slope, that means the M, which is our slope, will now be rewritten as slope at, well, okay, we already have that. So we have the slope, which is M, is equals to minus EA over 2.303 R. So we make this the subject of the formula because we are looking for what? That minimum extra amount of energy that is required by the reactants for a chemical reaction to take place. And that is the activation energy or the energy activation. So we can use this as a subject of the formula and cross multiply. And when we do that, it means that we can cross multiply. It means we have minus EA is equals to slope, which is M, let me write it as slope, times what? Times 2.303 times R. We can now fit in the values. So that means we have the slope, which is minus 20, no matter what was given to us in the question, multiplied by 2.303 times R. R is what? R is our gas constant. And if R is our gas constant, that means it will be 8.314 kilojoules, or rather joules. It is given in joules per mole per Kelvin. So this is a constant, the gas constant. Now if you take your calculator and do this multiplication, first understand that this negative sign and this one will cross out. So your activation energy will now become what? Multiply 20 by 2.303 times 8.314. What will you have? You are going to have a value that will give you 382.9 joules per mole. That is what you have. And this is what you have. But activation energy is calculated in kilojoule per mole. So you have to convert this to kilojoule per mole by dividing by 1000. And when you divide by 1000, what you have will be that therefore your energy of activation is 0.383 kilojoule per mole. And this will give you the extra amount of energy, that, or the extra minimum amount of energy that is required for that reaction A plus B to give you P to what? To take place. That's what it means. So your activation on the energy, which is the minimum extra amount of energy required for a reaction, for the reactants to effect a reaction, will now be what? 0.383 kilojoule. So it will have been simple for us to just go straight into using the Arrhenius equation, and then we do what? We just go and solve the problem. But you need to understand the roots of the equation, the roots of the problem. You cannot just jump into taking a formula and solve a problem. You should understand how the formula came about, and that is why I decided to take us through to understand what the question requires out of us, and then how we can do what? Solve it. I am sure that you have been able to go with me through this journey, and you have understood also how we can calculate energy of activation and what energy of activation is, and what the equation for the Arrhenius that describe energy of activation means, and what the terms also implies. Today has been a beautiful class. Do not forget to share this class. Do not forget also to subscribe. Tell your friends who you share this class with to subscribe. It's going to be a beautiful moment with them sharing with us what we are doing here. And also know that there is a Facebook page, Dr. B Chemistry Classes or Dr. B Science Classes. Share it and ask them to follow. Like, comment. Until next time, I remain Dr. B. It is bye for now.